right, thank you. Let me share my screen. Start presentation mode. Okay, can everybody see everything? Okay, all right, I'll start by thanking everybody. Thank you, Brahman, for the invitation. I will also start by saying I am an engineer, not a scientist. So although I have learned some about the Jovian system in Europa by, due to my work on this mission, I am not a planetary scientist. I'm an engineer. We build the things. We don't necessarily study the things. So I'll preface that and apologize for if there's any science questions that I don't know. And then maybe Brahman, I don't know. I can promise you I won't do a good job of managing a chat box and presenting. So if you could help me, if there are questions in the middle, if you could help me, that'd be great. But again, so my name is Jackie Perry. I work at the Johns Hopkins Applied Physics Lab, which I will forevermore in this presentation call APL, in Laurel, Maryland. We do a bunch of things. We have, there's like 8,000 or 10,000 people, but only about 1,000 do space related stuff, the bulk of which is civil space, so mostly NASA work. And so I am a harness engineer, and I'm the section supervisor for our harness development section, as well as Brahman said, the lead engineer for the propulsion module harness. We'll talk more about what that means in a minute, for the Clipper mission. So I would like to start by just talking a little bit about Europa and its history. So on January 8th, 1610, Galileo discovered 4 of Jupiter's moons, one of which was Europa, circled in the image down here. It's the 6th largest moon in our solar system, slightly larger than our moon. And in 2013, Hubble detected water vapor plumes coming from Europa that they thought were coming from cryogeysers. So then in 2018, people reassessed some data from the Galileo mission, which at that point had finished its campaign. And reassessing that data, they found data that confirmed that those geysers were there. That the water vapor plumes were there. So that just continues to kind of generate interest in what could be going on in Europa. So as far as we can tell, it has more water on it than all of Earth, which is a lot, if you, for me to think about. And they think that there could be liquid water under an ice crust. And water, why is that interesting? Well, water could have prebiotic chemistry or, maybe even life. And so that's a really interesting thing to think about. And so the image on the top right here is a diagram, not like an artistic image of what we think Europa could look like. So there's, the core and the inside of the moon, and then potentially there's an ice crust, but potentially a water layer underneath of that. And that's kind of what we want to probe at and see, is it there? And if so, what's going on? Okay, so that's Europa. So let's talk about the Clipper mission. So it is a partnership between the Jet Propulsion Lab in Pasadena, California, and the Johns Hopkins Applied Physics Lab, or APL, where I work in Laurel. Its launch date is currently 2024. It'll pass over Europa 40 to 50 times and collect data and eventually build a near complete scan of the entire surface of the moon. It will come as close as 16 miles to the surface, but most of its passes will be within 60 miles. So it's getting very, very close to the surface. The payload, which we'll talk a little bit about in the next bunch of slides, includes cameras, spectrometers, radars, thermal sensors, magnetometers. And with all of this data, they'll be able to compile high resolution images, compositional maps of the surface and the atmosphere, information about the presence of some subsurface water, magnetic field information, which helps them just characterize what's going on at the planet, and information about what's going on in the middle of the moon, what's happening at the middle of the moon, and then location of warmer ice pockets, if there are any, and then water plumes, and sky's the limit, I suppose, with what they could put together there. So it's a big spacecraft with a partnership. There's a lot of shared components. So where I work, APL, we are responsible for the propulsion module, which is the center cylinder here that you see. It's the entire propulsion subsystem. So a spacecraft needs a propulsion system to kind of navigate and get around wherever it's going. And so it's a biprop system. So it has two fluids that'll come together to help it move around. And so there's all the plumbing, really. The propulsion system, some propulsion engineers will say they're just plumbers. So there's the propulsion subsystem, the electronics that are required to operate that system. And then those electronics do a few more functions for the rest of the spacecraft. We have some motors that will rotate these large solar arrays. These are, in this image right here, they're stowed, but they need to be able to move around to be able to pick up the light from the sun. And then the propulsion module also hosts a few instruments and then some components for other subsystems on the spacecraft. APL is also responsible for the RF module. So they do all of the communicating with the spacecraft. So there's this high gain antenna that's 10 feet in diameter. It's very large. There are a few other antennas that are mounted at these clusters here. And then there's a plate that has radios and some other things that are used to send and receive data. We are also responsible for the solar arrays. These are being built by Airbus in the Netherlands and Autobahn, so Germany as well. But we are providing engineering, programmatic, and contractual oversight. And then the Jet Propulsion Lab is responsible for the avionics module, which is this cubic vault that you see. It's mounted to the top of the spacecraft. It hosts nearly all of the instruments, as well as internal to that are a lot of the electronics boxes that are kind of distributing all the power, kind of the brains. A lot of the main computer kind of stuff, reading data and things like that are in the avionics vault. And then the instruments that are kind of littered all over are provided by various institutions. And in a few slides, we'll talk about each one of these instruments so that you can kind of get to know them a little better. At launch, we will weigh about 13,000 pounds, and that's wet mass, so it includes the propulsion fluids. And then once the solar arrays are deployed, the spacecraft will measure 20 feet high and 72 feet from wingtip to wingtip, which is the span of a basketball court. So this thing is very, very, very large. Okay, so now we're going to go into a little bit more about each of the instruments, because that's why we're going, right, is to get the science for the scientists. But before I dig into that, I want to say these are screen grabs from the Europa Clipper website. I highly encourage you to go check it out. It's a really interactive website. So on the right here of each slide, you'll have a simplified model of the instrument that we're talking about. And on the website, you can move it around and look at it from all the different views. And then on the left, it shows you where it is roughly on the spacecraft. And when you're on the website, you can kind of zoom out and kind of, get maybe a better sense of where you are, as well as more information about the instrument itself. I'll also mention before I get into the details that you'll notice a lot of commonality between the instruments as far as the kind of questions or the kind of questions that they're trying to get to. And that's really because although every instrument is providing unique data and you can make discoveries from the bits of data from each instrument, it's really when they come together as a suite that they have the most bang for the buck. And that's really how you get the most holistic view of the place you're probed. So in this case, Europa. And so that's why you'll see a lot of that overlap. And additionally, if you think about scientifically, if you discover something with one instrument and it's confirmed by another or two or three, that just, it gives even more credence to the finding. And so don't be alarmed, I guess, if you see some repetitive things they're hoping to probe at. So we'll start with eThemis. Oh, the other thing I'll say is we love acronyms in the space industry. So you'll see a lot of these acronyms as we move on. Some of them are more and more of a stretch, but give us a break. We're engineers. And scientists. So the eThemis is Europa Thermal Emissions Imaging System. So it's a thermal imager. It'll produce infrared images of Europa at 3 different wavelengths, which will help them map the surface temperature. This instrument, I don't remember if I said this, is being provided by the Arizona State University. The next one is Mize, which is Mapping Imaging Spectrometer for Europa. That's a joint instrument being provided by the Jet Propulsion Lab and APL, where I work. And so this is another infrared imager. And the spectrometer will separate the infrared light into its various wavelengths that it can then use to map composition of the surface. The next instrument is the Europa Imaging System, or EIS. Sometimes people on the program call it ICE. You might hear it described either way. APL is making this one, and this is a wide angle and a narrow angle camera. And so these will provide high resolution images, stereoscopic and color images that will provide all of the things that you would expect out of imagery. Right? It's going to be really nice photographs to look at. The narrow angle camera is on a gimbal, so it's going to rotate on 2 of its axes, which will be also interesting. It gives them a bit more flexibility in kind of what they can see. Also uniquely challenging from the engineering perspective, or from the harnessing perspective for sure. The next instrument is the ultraviolet spectrograph, or UVS. It's being provided by Southwest Research Institute. And so this instrument is collecting ultraviolet light, and then it'll create images from that. And that will help them really probe the composition of the atmosphere and even some of the materials on the surface. The next instrument I'll talk about is REASON. Now this one's really a stretch acronym-wise. So it's Radar for Europa Assessment and Sounding Ocean to Near Surface. It's being provided by the University of Texas, Austin and JPL. And there's 3 on each wing. So 6 total radar instruments. And just like, for those of us in Maryland who maybe are used to water, like just in the same way as when you're out fishing and you use radar to find schools of fish and things like that, it's working similarly. So it's bouncing radio waves off of the surface, but it can even bounce them off of subsurface features. And when they come back to the spacecraft, the difference in when they come back and then how strongly they come back to the instrument will help them create a picture of what's going on. The next instrument we'll talk about is the Europa Clipper magnetometer, or the ECM. That's being provided by UCLA, University of Michigan, and JPL. So this is a suite of magnetometers. There's 3 magnetometers on a boom. Traditionally, or at least for the spacecraft that I'm more familiar with, the magnetometer booms are kind of rigid structures. This boom is kind of like a jack-in-the-box. So there's a can that's 18 inches in diameter or so mounted on the prop module, or a propulsion module, and the boom is coiled into that. And then it'll deploy and kind of pop out like a jack-in-the-box, but much more controlled. And the sensors and the harnessing are on that. And then those sensors will just continually monitor the magnetic field, both for strength and orientation. And so, it will do this as the spacecraft is moving around, and that'll help it gather information about the ocean itself, about, what's going on inside of the moon, even its atmosphere, ocean depth, salinity, all things like that. They can actually pick up information about just based on the magnetics. The next instrument is the Plasma Instrument for Magnetic Sounding, or the PIMS instrument. So this is being provided by APL, where I work. There are 2 of these on the spacecraft, one at the top, the avionics vault, and one at the bottom on the propulsion module. These are Faraday cups, so they will measure the current produced by plasma. Plasma is charged particles, and there's a lot of charged particles in the Jovian system. And so it will measure the density, velocity, temperature of those particles to help them kind of understand what's going on in that part of the Jovian system. Next, there's mass specs, or the mass spectrometer for planetary exploration for Europa. So this is Southwest Research Institute, their contribution to the spacecraft. Mass specs will collect gases and then turn them into charged particles, bounce them around, and then based on how quickly they move around, it can kind of back calculate what those atoms are, so that you can determine the composition of something by using a mass spectrometer. So that's what this is going to do. So it's going to, remember, we're getting really close to Europa as we pass by. And so it's going to be able to assess, as are all of these instruments, but they'll be able to assess the gases in the atmosphere as it's passing, making its many passes. All right, and so I think this is the final one, SUDA. This is the Surface Dust Analyzer. And so believe it or not, in space, it's not a ton of dust, but there is dust. And so especially when you're near a body like Europa, it's getting hit by things as it's traveling through space, little bits of dust or smaller bits of, rock and whatever that are out there. And so as they collide with Europa, they will, that rock will hit, you will get a blast of dust. This instrument will measure that for size, speed, and direction. It will also ionize it because it contains a spectrometer to then determine what particles are in those bits of dust that popped off of Europa, which will help them understand the chemistry of the surface. All right, so that's the instruments. So now we've talked about what Europa is, Europa Clipper is. Next, I kind of want to talk about what makes this particular mission difficult. I'll start by saying, so APL, where I work, JPL, NASA Goddard did the propulsion subsystem part, so the part of it. These three organizations have a tremendous history with making spacecraft for really challenging environments, right? Between those three organizations, we've gone beyond the solar system. We've gone to Pluto and beyond. We've gone into the sun. We've gone all over the place. So we can make hard things work. That being said, this is still a challenging mission. And so one of the challenges has been the radioactivity at Jupiter. So the Jovian system has a lot of radioactivity. So it kind of comes in two flavors. The first is total dose or total ionizing dose. So you can think of that as kind of if you went to the dentist and you got a dental scan and they put a little sensor next to your head. At the end of that scan, they can look at that and tell you, oh, you were exposed to this much radiation. So similarly, so that's a total dose. So I will say for for a medical scan, the most intense scan you could get is an abdomen scan. And the total dose for that is 0.07 rads, which is a unit of measurement for radiation. 0.07 rads. Under the thermal blankets, so spacecraft tend to be covered in these blankets to kind of keep portions of it warm for a spacecraft. And so underneath those blankets, which do not provide a lot of shielding, if you get rid of the margin, you're at 20 megarads. So that's 20 with 6 zeros versus the most you might see for an X-ray scan would be 0.07. So it's really, really intense, when you compare it to things maybe you and I are more accustomed to. And the trouble there is that a spacecraft is effectively a lot of metal and a lot of plastic. So the plastic is used as an insulator, right? The harness itself is conductors. If you think of the wiring in your walls, it's a conductor, and then those conductors have to be jacketed with something, and the jacketing is insulating. You can't have you can't have it be electrically conductive or you short everything out. But that plastic, depending on the material, it might not survive in that environment because the total dose is so heavy. So the other type of radiation that Jupiter and therefore Europa just showers us with is the flux environment. So flux meaning the rate of the rate of the movement of the particles, the charged particles. And so they can, when they're moving really quickly, they will kind of start to build up in those plastic materials. And depending on the material and then the thickness of the material, they'll build up and build up and build up and build up and build up until that particular configuration cannot handle it anymore. And then it will discharge. Now, if it discharges to a metal bracket on the spacecraft, we don't care so much because it goes to ground, the spacecraft ground. But if it discharges onto a wire and then goes to the end of the wire and then into an instrument or a component on the spacecraft, an electronics box that does anything at all, really, it can blow that box. And that can take down worst case, can take down the whole spacecraft. Best case, which is still a terrible case, it could take down one of those components. Additionally, those components, if you think of your computer that you're sitting in front of right now, it has a lot of printed wiring boards, which are just plastic and then traces of copper. And then on top of that are little components, which are often in some kind of an insulator, maybe some ceramics, but then metal. And sometimes then those are coated in a plastic. So there's a lot of plastics. And so if it were to build up on these plastics and discharge into one of those traces or one of those components in your box could fry. And the solution to all of these things is to shield. In the same way that when you get that dental scan, they give you the lead blanket to wear so that parts of your body that are not, you don't need to get scanned, don't get exposed to radiation. That's the same concept we use here. They use lead because it's really dense, so you don't need as much of it to give you a lot of protection, and it's nice and dense and gives you a lot of shielding. So similarly on this mission, our electronics are all very heavily shielded behind tantalum or titanium, which are really dense metals. So you can use maybe a thinner amount of those, or very, very thick walls of aluminum, or sometimes both. Sometimes there's a layer of tantalum and a layer of aluminum. But lots and lots of shielding. If you can keep the radiation out, you'll do better for yourself. The harness and the cables, so the stuff I work on, these are all wrapped in, oftentimes on spacecraft, it might be aluminum, if it's wrapped at all, depending on the electromagnetic interference requirements. But on this mission, they're wrapped in copper and lead and sometimes multiple layers of copper or lead or both. So there's a lot of shielding because we're trying to keep this environment out. Because Murphy is never a friend, if a material does really well in the total dose world, it does not do so well in the flux environment and vice versa. And so as an engineer, we are all, no matter what our hardware is, trying to do this dance where we don't want to over-engineer, because if you shield too much, you weigh too much. And every spacecraft ever is mass constrained. They want you to be as light as possible. So we can't just say, well, I'll just put all this lead on there and call it a day. We have to shield just enough plus a little margin and call it a day. So that's been a real struggle. But we have, we've come up with solutions and implemented them, but it was hard to do that dance. Another struggle that we've had is just this cross-continent and international partnership, just the logistics. So if you think about, I work traditionally 7:30 a.m. to 5 p.m. When I leave at 5, JPL on the West Coast, it's still 2 p.m. So they still have a good chunk of their day left. So we don't have a lot of overlapping time. And then if we throw in Airbus because we're trying to have a conversation about the solar arrays, well, now it's even harder because they're so far ahead. So if we have a 9 or an 8:30 a.m. meeting East Coast United States time, West Coast is 5:30 a.m., Airbus is 2:30 p.m. So that alone can make it very difficult to co-engineer, and to kind of find good times to quickly resolve issues that are coming up. And then the last thing I'll mention that was unique for this mission, at least for the missions I've worked on, are the Planetary Protection and the Contamination Control requirements. So I'll start with contamination control. That just means how clean you are from a kind of a dirt and dust and outgassing perspective. So every spacecraft has contamination control requirements, but this mission, because of some of our spectrometer instruments, they are so sensitive that everybody needs to be super clean. And so what that meant for our hardware is a lot of extra processing to just get, plastics tend to, and some of the other materials we use, they tend to just kind of outgas quite a bit. In the same way, you get a car, the new car has the new car smell, that's outgassing adhesives and stuff. We have that too. And so you need to get rid of all that, because otherwise the spectrometer is going to say, oh, this adhesive is here in Europa. And of course it's not, it was just in your hardware. So we need to get rid of all of that. And it was, like I said, the requirements were much stricter. So we had more work we had to do. We also, at APL, we fabricated the prop module harness in a clean room space to try to help with that. Then there's planetary protection. So this is not the Armageddon, don't look up situation. That's planetary defense. This is planetary protection. So in the 60s, there was an international treaty signed when the United States started, trying to get to the moon, that said, if anybody brings anything home from a place and we think there could be life on there, we will do everything we can to sterilize or isolate it so that we don't bring alien bugs to Earth. Similarly, if we go somewhere, we will do everything we can to not take an Earth bug to that place. So in this case, you'll never get 100% clean, but because you can't autoclave this like you can like lab equipment or something. But you can get it super, super, super clean. So there are very strict requirements on this. And so what that means to hardware owners is we have processing in these bakeouts and lots of cleaning. And we are in super, super, super clean environments, which has been great during a global pandemic because going to work was the safest place I could be when I was in these clean rooms. So, but those requirements, we have to be extra careful in this case. Now, I'll say there is no plan to land on Europa for this mission, but there is a fault case, so like a worst case situation where we could end up there if things went wrong. And that's how conservative NASA is, where they're like, well, even if it's a possibility and we think that there could be prebiotic chemistry or even life there, we don't want to risk sending an Earth thing there, because the last thing we want to do is, put water bears on Europa. So, so we'll do what we can to keep this as clean as possible. Okay, so what's a harness? Now that we talked about what's Clipper, what's Europa, what's hard about it, let's talk about a harness. So a harness is a complex system of connectors and wires that connects critical flight hardware. So if you think about, I don't know what your computer system looks like right now that you're plugged into, but you probably have a bunch of cables connecting monitors and things. It's like that, but significantly more. So at a spacecraft level, they can be as large as 400, 500, 600 connectors, tens of thousands of interconnects, or what we call contacts, thousands or tens of thousands of feet of wire. So they're complex. The image you see here on the left is the main harness from the Van Allen probes prior to its bakeout, so not installed in the spacecraft. The image in the middle here is the interior and main harness for Parker Solar Probe. So the spacecraft that just recently got into the hottest part of the sun. And the one on the right here is the Europa Clipper propulsion module harness. So you can see we're pretty because we're covered in copper. We're heavy, but we're pretty. So this is a silly little crash course on how to make a harness. So you get some wires, you smush them together. You throw contacts on the end, whether it's crimp or solder. You shove them into a connector. You throw on a back shell, wrap it up. You don't really use Reynolds wrap. That's just a joke. And then you test it and you're done. But it's really not that easy. The devil is in the details here. We have to worry about proper routing. So what I mean by that is we know we have to connect this thing to that thing. And there's 1,000 obstacles in the way. So we have to route our wiring and our harness to that location appropriately. I won't get into what that means, but there's a lot of requirements and things you have to jump on. We have to choose the right wire. So not all wire is made the same. Not only do we worry about that jacket, the plastic insulating material, to make sure that it'll survive whatever environments we're going to, whether it's really cold or really high radiation. We have to choose that. We have to pick the right gauge. The gauge determines how much current you can pass through it, which plays into a lot of kind of the power that you're trying to distribute to heaters and deployment mechanisms and instruments and all these things. So we have to make that selection, and it's very individual. So we don't have the same wire across the entire spacecraft. It is specific to this function that I'm sending from here to there. We have to pick the proper connector selection. And to some degree, sometimes that's a little easier because a component will say, I'm using this connector. And we say, great, I just need to find the one that mates to that. Perfect. But we have to worry about that insulating material. And maybe we have to customize something about it. So there's always some gotchas in there. The images you see over here, this is a micro D connector. So we have a penny. I have a penny in the picture here just for scale. They're very tiny. We might have a bunch of vendors for these parts. We have to pick parts from qualified vendors that we know will give us robust parts. This second image here, these are what we call D-sub miniatures or D-sub connectors. And then the bottom are military spec circular connectors. And we can use any of these flavors and even custom ones beyond this. These are just kind of common parts. We have to choose the right back shell. So these big metal pieces on the back, we call these back shells. They not only protect the connector and the wire joints, so wire would come in the backside here, much like you see here. So they don't just protect that joint, but they give us a place to hold on to, right? Like a human is putting this connector and mating it to the component that it mates to, or the instrument it mates to, or maybe the other connector and cable that it mates to. And you need a handhold so that you're not too rough. But the geometry of this, we have to put our mechanical hats on and think about that and make sure that it doesn't physically interfere with anything nearby. We sometimes have to accommodate jumpers, which are just loop backs, kind of like what you see here. Sometimes they include a component, a resistor like this. Sometimes the resistor has to be somewhere in line in the cable, and we have to find a safe place to put it where it won't be susceptible to damage when we are integrating everything and moving things around. So we have to think about that. We have to think about the overwrap for either radiation shielding, which we talked about, or electromagnetic interference. So that's really just about keeping the noise down. If you think about, I don't know if you ever, I feel like this doesn't happen so much anymore, but back when I had a landline, I could be on the phone and I might pick up my neighbor's phone call. That's noise, that kind of noise that you might get. Shielding can help keep the noise out. And if you're a noisy function on a spacecraft, you can keep your noise to yourself. So picking the right amount of overwrap for that and shielding. We have to worry about proper grounding, which is just any kind of electrical circuit will need some consideration about grounding. And then putting this all together has to be done by extraordinarily skilled and capable and trained technicians. They are very, 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 very highly trained to make sure that they build this and it's durable and it's functional. People can take a few years to get to the point where they are what I'd call like certified to work on flight hardware. These things are also pretty small. I don't know if you can tell this from like the penny pictures here, but I took a soldering certification class, and what I learned is no one should have me solder anything. My soldering is not great. These people their fine motor skills are amazing. And then we have to follow proper traceability and record all of these things appropriately, because there's a whole set of quality engineers that expect us to prove that we did it well. We're using all of our taxpayer money. So, we need to prove that we're doing a good job. And so we also have to just keep meticulous records of everything. So what is the propulsion module harness? On the right here, you hopefully see a spinning model of our 3D CAD of our harness. We are essentially all of the harnesses and cables that go from some brackets at the top of the propulsion module that interface with JPL and their portion of the harness, to all of the components that are on the prop module. We will weigh, I expect, about 137 pounds when all is said and done, just our harness. It will span, this entire cylinder plus the secondary structure, so that the pink lines you see kind of sticking out. Anything that's kind of mounted on that main cylinder, we call it, if it's a mechanical piece, we call it a secondary structure. So that cylinder is about 10 feet tall and 5 feet, just the cylinder is 5 feet wide. And as you can see, our harness kind of goes everywhere. So how did we make this? Well, first, we create electrical designs that incorporate interconnects for every component on the spacecraft, or in our case, every component on the propulsion module. At the same time, we developed a 3D CAD model of our harness in the same way that, people made the mechanical designs for all the parts that are in gray on this image. And then at the same time that we're doing that, we're procuring all of those parts, the wire, the connectors, the contacts, all the other kind of consumable bits that we need in fabrication. And then you have to design and build a full-scale fabrication fixture, or what some people call a mock-up, that you'll use in assembly. As you can imagine with the imagery that you've seen, we have complex bends and we're wrapping them. If you wrap something, it stiffens it. So you need to wrap it in its weird shape. If you try to wrap it, flat on a bench and then bend it in that weird shape, it's never going to work. So we have to design and build this. And then, of course, when it comes in, we have to certify it because it could have been made wrong. So once we have all that done, then we can start fabrication. So we start laying in the wire, terminating it to contacts, eventually wrapping and all that. 9 to 12 months later, your harness is finally ready to test. Testing takes 3 to 4 weeks, the first go round, and it will verify that all of our interconnects were done correctly to our drawings. And it will make sure that nowhere in those runs do we have any kind of shorts. And if that is found, then we have a rework process to correct. Once it's tested, it's ready for the bake out. So as you might recall, I mentioned a contamination control and a planetary protection bake out. And so we went into this giant chamber. This is a picture of us on a bake out fixture. Doesn't look like this, it's a little different. And then it's bagged and it's sitting on a door, but the door is more like the floor of this giant chamber that's, I don't know, probably 12 or 15 feet tall. It's kind of shaped like a pill. So the floor lifts up and goes in there, and it baked for 144 hours, I think, which is much longer than we normally do. But once it comes out, it is very clean from a contamination standpoint and very, very, very clean from a planetary protection standpoint, and is ready to integrate onto the spacecraft. So that's how you make it. We are a small team at APL, but we've done a lot of work. So I'm going to, for the sake of things, call every person by name. So this is Mia Harvey. She is our electrical designer. She's made a lion's share of our electrical designs. Devin Hahn has done all of our the 3D CAD routing modeling that you saw. Carlisa Drew is our very skilled lead technician. She built nearly all of this harnessing herself. And then for a while, we had a second technician, Boris Sayasena. He helped us for a bit. And then at some point, we added an engineer to help us with test named Jaime Avendano. He has tested this hardware multiple times over and wrote all of the test code. So that's our team. In case it seems like they're real easy, harnesses are harder than you might think. It's not just wires and connectors. Throughout that one-year build campaign, many things can change, and the harness has to respond. So electrical boxes could change their interconnects. They could change their connectors. They could change their whole mechanical design. And we have to respond. The spacecraft system could change the layout of things because of maybe an issue that came up. We have to respond because we have to hook those things up correctly. The spacecraft system or one of the components could find a problem when they're doing tests. And so they look to harness, there's a phrase, fix it in the harness. It is far less expensive for us to respond and fix it than to have one of those boxes do a repair. We are although we call ourselves a subsystem, we are hardware that lives at the spacecraft system level. We never exist on our own. So we're very intertwined with that larger spacecraft. So anything they need or any change they have, we often have to be flexible and roll with those. And so that can be hard if you're a planner like me, but it's just part of the job. So when it all goes really well, it's a thing of beauty. So this is a time-lapse video of our installation onto the propulsion module. So this 80-20 frame that you see here was our bakeout fixture. And so you can see we are heavily gowned up with masks. That's, even had we not had a global pandemic, that's what we would have worn to be in a planetary protection constrained clean room. So we came out of the chamber. We have moved to a totally different building. We have debagged, and then we will crane onto this installation cart and install that. Took about a day beginning to end, but you'll see the whole thing in about 30 seconds or 60 seconds. And then we are doing our thing, and over in the corner, there's the RF module in that other view. So we were sharing the space for a bit. So the cart comes forward, and then you'll see us all get into place, and we will slowly cut the harness because it's just kind of temporary, like with zip ties, really temporarily tied onto this frame. We'll cut the ties and we will start kind of lifting this giant harness and kind of sliding it over. And we had pre-bonded, they're called tie downs. They're just features that you will literally tie the harness to. And so we kind of moved it over and started tying it up. There it is. Now she's on. All right, I think I'm going to pause it now because it's effectively done. That's the end of it. And then I think I don't know, should I keep the screen up? Maybe I'll keep the screen up so I can go to other slides if needed, but that's all I have. So I guess I'll open the floor to questions.
Thank you, Jackie. I feel like I just went and it was a dissection of a spaceship. It was wonderful to see the internal workings, something that we don't get to see or appreciate. And we do have some questions here. One is how long, the launch is in 2024. This is Kenneth. How long is it expected to take to reach Europa? Do you have that information?
Oh, I should know this. I do not recall off the top of my head, but I can Google it. I don't remember. I apologize. I do not remember. Okay.
And then Lisa wants to know how long did it take to build this? I think you mentioned it, but
so for our part of it, the harness, the prop module harness only, it took about a year from beginning to end for fabrication. If you talk about the whole spacecraft and we're talking just fabrication, and this mission is unique. It's intentionally phased, staggered a bit so that APL goes first, and that was intentional, and JPL is staggered and they go a little later. Normally a full spacecraft fabrication all the way up till where integration starts is probably about a year, maybe a year and a half. And then you have maybe 9 to 12 months of integration and test, or assembly, test, launch and operations, people call it different things, where you're testing the whole spacecraft system. And that leads all the way up to putting it in the fairing on the rocket and letting it go. On this mission, we deliver to JPL, the propulsion module, in April. Well, we ship out in April, so we hand over the keys in May of 2022. And then JPL will add their parts to it and continue to test and add and test and test. And then that'll take them, you're effectively testing all the way up until they put the fairing on, which is, the last week or two. It's not very much time. So yeah, that's that kind of all comes together at the end. This mission will go. So if I started about a year and a half ago and it goes till 2024, what year is this even anymore? So maybe what's that, like three years maybe of fabrication.
And Nicholas asks, will you provide any support during the in-flight mission, or does your job end once the spaceship is delivered?
That's a good question. For harness engineering, at least at APL, I can't speak for other organizations, but at APL, we are very much a cradle to grave kind of organization. And so when I'm on a mission, typically I start really early. So I'm answering more than the question. I start early in requirements development, which is kind of sometimes phase A, but like phase B, very early. I don't know if people are familiar with NASA phasing, but early on requirements development. What are they even asking me to do? All the way through design, fabrication, testing, installation on the spacecraft, and then even into integration. So at APL, our harness engineers often, because there's always something that comes up when they're like, oh, I better call a harness engineer. So the harness engineer, at least one, and a technician will stay on really all the way until launch. And so like on Parker Solar Probe, we launched out of Kennedy in Florida. I was in Florida maybe a month or two before launch, and then I went back for launch. So you're really, now once it's gone, you leave it up to the mission operations team to, get where they need to go. And there's not much you could do, right? If something went wrong, we can't fix it. So, which is why we test so much. But yeah, harness engineering will go at least APL will go like all the way up till the very end. We are working on it, even if it's just on call near the end there, just, to answer questions if they see something funny in test, and it's easier to call and ask a question than to try to dig through my drawings, right? Just call and ask.
Right. And Alexi asked, are the harnesses made domestically, like all the components, not the finished product?
So the components for NASA missions, there's usually a requirement that they be domestically produced. Now, is the raw, the raw gold that goes into some of the contacts, I don't think they go to that level, but certainly like every connector I buy, they tend to have to be American companies. I think there are some exceptions, but NASA has kind of a tight regulation on, because they don't want to have to worry about counterfeit piece parts, I would call them. Sometimes things that are made that are inexpensive fall apart, and maybe they'd be fine for your cell phone, right? Or like if you're doing a fun little Raspberry Pi project in your house. But they just won't survive the launch environment. A launch has real, it's like being at a KISS concert times 100. Like the acoustics are really bad, and then the vibration is really bad, and shock from separating from the spacecraft is really bad. And so then it's whatever the environment is when you get there. So all of that, you need a really robust part. And so they tend to keep those very tightly constrained. So yeah, oftentimes American-made base parts. Now, assembled parts, like APL, we have the capability at APL to build all of our own harnesses. So the only reason we would look to another company, and it would be a domestic company, to make a cable or harness is if like our technicians are just swamped because we have so much work. But by and large, we make everything even on site. So not just domestic to the country, but like in Laurel. Oh, I can't hear you.
Sorry. Nicholas says Europa should arrive April 2030.
Thank you.
Here we go. Got a long trip ahead of it.
Put it in your Google Calendar.
Right, exactly. Shireen says it's an absolutely fascinating look at the gut of a space probe. We need more space engineering talk. Yeti says, do you get involved in balancing and common mode rejection?
I do not. So I do not. I'll just say that.
Okay.
Is it because it's all final stage sort of digital assembly to always be earthed, or is there any analog component in that that is still using?
Go ahead. Sorry. There are analog. So there are functions that are digital and functions that are analog. But from the harnessing perspective, like that kind of stuff tends to happen at the electronics box or the instrument, or the thing that has active components. A harness is not is more passive, right? And so the most we worry about with kind of hardcore electrical engineering work tends to be things like derating of our wiring and shielding, but we work really closely with EMI engineers to make sure that our implementation on the hardware side, based on previous tests and everything, are going to meet their requirements. And then sometimes you don't know and you make a best guess, and then in tests you find you need to compensate more, and then you can add shielding effectively is what you end up doing. So yeah, we have a lot of active stuff in a harness.
So I mean, there's effectively it's all unbalanced then.
I don't know if I would say that. I would say I don't know enough about that world to know if at the system level it is balanced.
Yeah. I mean, it's I mean, you're not going to be getting involved in sort of like the complexity of the wiring arrangement within the spherical arrangement for conductance, but you'd expect it to send both a signal in a positive and a negative, so there's a backup, so you can find out if there's been interference from something on the wire.
Certainly we have twisted pairs, right? And so for every active, there's a return. So certainly we have that always, yeah.
So there is some element of balancing going on.
Yeah. I forgot about that because it's like so standard. I forgot about that.
Sorry, a bit geeky into analog electronics.
I don't mind geeky.
No, we welcome that. Well, let's see. Alexi wants to know, can you tell us a space harness joke?
Ooh.
One that...
I don't know. Can I? Should have asked ahead of time. I know lots of dumb, dorky jokes, but I have a good Heisenberg joke, but I don't have a harness joke. I don't. Oh, I feel like I failed you.
Oh, well, you can get it. If you think of one, let me know. I'll pass it along to folks.
I will.
Kara asks, will there be carryover from the Clipper to the lander mission?
We were hoping. So right now, lander is a bit of a pipe dream. There's not dedicated funding for it. It was taken down to a very low level. I don't know, all time seems the same these days, but two or 3 years ago or something, maybe 4 years ago. So I don't know. But in the perfect world, yeah, we would take what we learned, both from the hardware development side, so kind of the things I focus on, as well as even the science, and push that forward, for a lander mission. Yeah, that would be great, but time and budget will tell. And NASA priorities, you never know what the scientists will be into it from the next decadal study.
Absolutely. Let's see, we have Jeff. How common is getting late recs, and how do you have an example?
Late recs, like requisitions? Oh, requests. Late requests.
Requests, yeah, maybe requests.
Oh yeah. How common is it? Fairly common. So I would say, so when you're making a harness that takes this long to make, it is inevitable that, because we're all making at the same time. So if you're a hardware owner, an instrument or a box, they make a breadboard, which is kind of quick and dirty, just concept. You're proving a concept. Then they make an engineering model, which is like, okay, I proved I could probably do it. Now I'm going to use much better parts and I'm going to really test it. And then when you get to that, theoretically, your flight build is smooth sailing, but that's theoretical. And so they're building their flight and like, you don't know what's going to happen. And a thing happens. And they can't help it. And we are building at the same time they are building. And so it's one of those trades that the program gets to make. And sometimes it's not even worth, discussing as a harness engineer, even though I would prefer no changes after we start fabricating. I understand that sometimes it is for the betterment of the spacecraft if I just eat it and we change. So I don't have a number for you, although I love numbers, but I would say it's fairly frequent. It's fairly frequent. And they're rarely major changes, but there's always just little bits of things that happen. And then sometimes even at the spacecraft level, a thing happens and the entire team has to respond. And if the simplest, quickest solution that gets us to the launch pad at the same time is for Harness to fix it, by all means, Harness will fix it. We're real dedicated, but like as a whole spacecraft team, everybody tends to be real dedicated.
Well, and speaking of the launch pad, how do you celebrate on launch day?
Well, it probably depends on whether it's, the time of day of the launch. So Parker Solar Probe launched at it was in the middle of the night. It was like 1:30, 2:30 in the morning, something like that. And I had my, at the time, 3-year-old with me and my husband. So she launched, we cheered, we went home and went to bed. So, and then the next day, there were program parties because when you get to the launch campaign, they call it at the launch site, the integration team tends to be there for a while, a few months. And so they're getting, long-term rentals or they're staying at a hotel or something for a long period of time. So they've been there a while. So maybe they'll host a little gathering at their house to celebrate. Certainly if you're still in Maryland when it launches, APL will often have a launch party. So we just, right before Thanksgiving, we launched the DART mission or the DART spacecraft out of Vandenberg, California. And for those of us that weren't working DART, so that was 10:30 West Coast time, but it was still 1:30. I think it was 1:18 in the morning or something, or 1:22 in the morning, East Coast time. We could have gone to APL at 1 in the morning and they had food and drink and it was very exciting. I did not go to APL 1 in the morning because I have a now 6-year-old. So, but I did wake up and turn on the computer and I watched. But I think if I had a launch that was at a reasonable time of day, I think I would have a get together afterwards, but I haven't had that yet. So.
And let's see, there is a request for your Heisenberg joke.
Oh, okay. Okay. So I will explain the uncertainty principle so that everyone will laugh in case people don't remember high school physics. So the uncertainty principle is that you can never know the speed and the location of an electron at the same time. You can know one, the other you can't know both. Okay. So Heisenberg's driving down the road and he gets pulled over. And the cop says, "Excuse me, sir, do you know how fast you were going?" And he said, "No, but I know where I am." Get it? I mean, it's not great, but that's my Heisenberg joke.
I've got a bad
Pierre?
one for you. How do you calculate resistance?
I don't know.
Oh.
Ohm's law is just futile. Yes, it's a bit tricky.
That's good. That's good. That's good.
How old were you when you first saw Jupiter in the telescope, and did you see moons? This is from Pierre.
Me? Oh, so
Yeah.
I haven't, the telescope I looked in wasn't strong enough to see moons, but it probably 2 years ago. So I was not someone who grew up thinking I want to work in space. I work with a lot of people who were that. I just by really good luck and hard work ended up here. And I will never leave because it is the most interesting and exciting and fun group of people to work with. And the programs are, even if my little bit isn't all that exciting, the overall story is exciting and what we get to partake in is really cool. Yeah, but I didn't see Jupiter for the first time until a couple years ago.
And Alexi says, do you enjoy automotive harnesses?
So my brother-in-law is an automotive engineer for Honda, and I try to geek out with him about this, but I don't think they're nearly as complex. So the conversation only goes so far. But I would love to geek out with an automotive engineer who knows about automotive harnessing. I would love that.
All right, do we have any other questions for Jackie this evening? In our fascinating look on the inside of spacecraft that are out there, that are out there, and the ones that are getting ready to be out there, going to Europa. You've seen the inside. What's your favorite connector type, Alexi?
That's a good question. I mean, everyone loves a good circular, a mil spec 38999, I think. They are robust and scoop proof. What's not to love?
All right, and on that, I think we'll end it for this evening. Thank you so much, Jackie.
Yeah, thank you.
A fascinating presentation, and we appreciate all that you and your team are doing to help expand our knowledge and understanding of space. And we're so grateful for your expertise and time that you give to us as a community. Thank you.
Thank you for having me. This was fun.
And thank you to everyone here tonight. Continue to stay safe. We hope to see you soon at another presentation online, or hopefully cross our fingers in person. We are working on our, some weather issues have made our field trips a little bit crazy right now. So we're rescheduling those, and our in-person things are being pushed back. But we will continue to learn together, come together as best that we can, and learn, and then take our knowledge and make other people smarter. So thank you, everybody. Take care, stay well, stay curious. Take care.
Thanks, Jackie. That was very interesting. Enjoyed it.
Thank you very much.